Resonance, we made it through the first sheet. Resonance stabilization of cations. Not quite sure where we left off. Did we do resonance of these here? Just the first one? Okay, stabilization by a lone pair. How do you stabilize a cation? Move electrons towards it or away from it? Towards it. Resonance structures for this. Do we have electrons we can move towards it? In this case, we actually have two sets of electrons. Windshield wiper. These electrons could move towards here. Windshield wiper. That would give, I'm going to go this way, resonance arrow. Double-headed resonance arrow. What does this electron movement give? We now have pi bond here, and this is going to have to be a plus over here. There's two H's there, there's two H's here, there's only 3 bonds of that carbon. There we go. That's a resonance structure. We can get another resonance structure. I'll label this as A, and this way going A. We also, right here next door, have a lone pair. These electrons can move in and make pi bond. I'll call this B, and going this way, we have the result of the B arrow. Now we have double bond between nitrogen and carbon. That's a plus charge. Two additional resonance structures, total of 3. What have we done to the charge? Terminology, we have delocalized the charge. Because the resonance hybrid, we could look at that. Resonance hybrid, there's kind of a bond and a half through here. There's actually a bond and a half through here and here. We have partial plus here on the end, partial plus here, and then partial plus here. This is a true structure. Thus, we have delocalized the charge. The charge is not just right on that single carbon. The charge is spread over 3 atoms in the hybrid. So charge delocalization. What's the major resonance structure up here of these 3? Major, right here. Why is it major? More bonds. What's another reason? All atoms with octet. The nitrogen has an octet. Here the carbon has no octet. Here the carbon has no octet. This is your major resonance structure. So if you had to say that the hybrid looked like which one the most, it looks like that the most. Kind of like the kid looking more like mom. Because mom's more stable. NO and X, X being halogen, always must have an octet. It has an octet. If it has an octet, it doesn't mind becoming plus. Let's go back to week 1 and 2. What type of orbital is that lone pair in?
P orbital.
P orbital. Why? Because there's a P orbital here. Anytime a lone pair is next to a P orbital, it's going to want to be in a P orbital. That's sp2 with an empty P orbital. That's why we learned that back during week 1 and 2. We have this P orbital interacting with that P orbital, making the pi bond, which we see in this resonance structure. What's this stuff called? It's called delocalized bonding or pi bonding. Resonance. Okay, let's look at how resonance can affect regiochemistry of maybe addition reactions. If you take this alkene reacting with HBr, which alkene do you expect? Well, the answer here is you're going to get the most stable carbocation. That will be the intermediate. Wherever the carbocation is, the Br attacks it. Would you rather have a plus up here or down below? Now it looks like they'd both be sort of secondary. Let's look at it. I'm just going to draw the two different possible cations. I can put plus up there, new H here, then methyl. This is where these came down and attacked H, left plus up there. Or we could put new H up there and plus here, where the electrons broke away from the bottom carbon and went and attacked the H, leaving the bottom carbon as plus. Which cation looks more stable? That one or this one? This one. What can you do here? Bam. Resonance. Electrons in. Get an alternative Lewis structure. Plus charge on nitrogen. Can you draw a resonance structure of this? No. There's no p orbital here, no p orbital here. It's an isolated carbocation. No resonance. Resonance. Which is better cation? Isolated cation or resonance delocalized cation? Resonance. Plus charge sitting right on one atom. Here the plus charge is spread over two atoms. You could draw the hybrid. There's a bond and a half between here, partial plus on nitrogen, partial plus on carbon. You got to know that the true structure is the hybrid. Resonance delocalization of charge. Which product's going to be formed? That one there. Br minus. Then adds the cation. You can always work with any resonance structure. You can get the final product by adding Br to this resonance structure, or we can add it to here. If you do it over here, these electrons add here and push these over. Add them there and push that over, you also get that. You can always work with any resonance structure. Because remember, in actuality, neither one of them is true. These are really fake. The true structure is the hybrid. Now we can say which is major, which is minor. Of the two resonance structures, which is major? This one. More bonds. One below, which product do you envision being favored? You react this alkene with HI. Would you rather make carbocation on left or right? Correct. H plus, I minus. UH added here, plus there. Why is that plus better than putting plus over on the right? Starts with an R. You see the resonance? We did resonance like this last time, right? With the benzene ring. Windshield wiper. Move them up. Resonance arrow. Boom, 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 UH. We can draw additional resonance structures. If we had added the H to the other carbon, UH here and plus there, is there any resonance possible for this carbocation? Why not, Hama?
Because it's too far away from the bond on the benzene.
Right. There's no p orbital here, no p orbital. What is resonance really? It's conjugation of p orbitals is what it ultimately is. I mean, here you have p orbitals all the way around this ring. And then you could say this is sp2 with an empty p orbital. But is this p orbital conjugated with these? No, there's no p orbital here. So you can't do this thing of resonance that we're doing. Remember the theory we looked at? The theory is ultimately p orbitals conjugated, becomes one system, and the electrons are just in there any way you want them. This is not conjugated with this, it's isolated cation. This is a delocalized cation. Charge delocalization via resonance. So which product are you going to get, left or right? The iodine will add to the cation that's formed. Now you might ask, why does iodine not add here? I mean, you could show a product with iodine here. Well, that product would not have the aromatic ring. You want to keep the aromatic ring, so the iodine actually adds to the original. Later on, the handout I just gave, the nucleophile may add to another cation that you get by resonance. But if you're dealing with benzene ring, you typically want to maintain the benzene ring with 3 pi bonds in the ring. Questions about resonance stabilization of cations? Move electrons towards it. You're either going to have pi bond to move towards it or a lone pair to move towards it. We did them both in this example. Next, we'll look at resonance stabilization of anions. How do you think we stabilize an anion? Do we move electrons towards it, or do we want to move electrons away from this atom? Yeah, this carbon doesn't need more electrons. That's not going to stabilize a minus. It's going to make it worse. So we would never move electrons towards it. And if you think about the orbitals there, that's also quite bad. There's no rationale for that in terms of structure and orbitals. Move electrons away. These electrons, need to practice on that. I still see mechanisms with arrows going all over the place. And clearly not starting by saying these electrons. Looks like some of you are starting by saying this atom. Or this, I don't know what. Every time you draw an arrow, say these electrons. And if you can't identify what electrons you're talking about, then you're not on the right track. These electrons can move into here. Now this is what I call in and out. I can't just make a bond here because that carbon can only make 4 bonds. I can't make a 5th bond. I can move these in and move these out. What would that give? Here I'm making a pi bond. Here I'm kicking these out onto that atom as a lone pair. And that's going to give pi bond. What's on this carbon here? There's the lone pair. Now that's minus. And there's a resonance. Let's take a minute and look at structure here. We have 3 carbons. I have a pi bond, so I'm going to draw there's the pi bond. What's the hybridization of this carbanion with the lone pair? I'll redraw it. What's the hybridization of this? How many H's on that carbon? Two. If there were 3, you would have 10 electrons around that, and you don't do that. If there was only 1, then it wouldn't be a minus charge. So it's 2. What's the hybridization of something with 3 bonds and a lone pair? Particularly this one. Who gets you? sp2. Why is it sp2? In Gen Chem, you would have predicted sp3 for this. Because anytime a lone pair is next to a p orbital, going to be in a p orbital. Have you ever heard that before?
Yes.
Good. Okay. There's a p orbital here, and it's got a lone pair. Why? Well, it wants to interact with this p orbital. And now you have one conjugated system. How many p orbitals in the system? 3 p orbitals. How many electrons in the pi system? 4 electrons. It's got 1 extra electron, so that's why it's a minus charge. There it is. It's a conjugated system of 3 p orbitals. It's got 1 extra electron. It's a minus charge. Here we go. We can back up to theory and say, okay, there's your 3. Put 4 electrons in there however you want. Let's put 2 here, 1 there, and 1 there. Well, that's what I got right here. I can put 1 there, and 2 here. Well, that's the original. You could actually also put 2 here, leave that empty, and 2 there. What would that look like? That would be minus, and that would actually be plus. That's actually a resonance structure. By the way, the net charge of this is minus. The net charge of that is minus. What's the net charge of this? Yes, if you look at the golden rules of resonance, every resonance structure has the same net charge. That one is so terrible I would never show it. Why is it so bad? 3 charges. Okay, you could get to that by polarizing this pi bond, making it minus and plus. Typically, you want to delocalize your charge. If we did that, we wouldn't do anything with the charge. It'd still be minus on the end. That's just not a good resonance structure, although it is actually a resonance structure. Let's stick with these 2. Which one's major, which one's minor? They're the same, equal contributors, 50-50. That is, the true structure has bond and a half here, bond and a half here, partial minus, partial minus. If you could look at this anion, it would look like this. There's not a full minus on that carbon, it's spread out on both. The bond order of each is 1.5 exactly. This carbon-carbon bond length and that carbon-carbon bond length are identical. You can't say, wait a minute, that's a double bond, that's a single bond. Well, for this structure, which is fake, the true structure is this. Draw resonance structures of this. This is the anion of phenol, called a phenoxide. Again, with cations and anions, one of the major goals of resonance is to delocalize the charge. Then, how do you stabilize an anion? You don't move electrons towards it. You want to move some of those electrons away from that atom. There you go. Draw resonance structures of this. These electrons move in here, these out. Sort of the in-out. What does that give? We now have double bond between carbon and oxygen. 2 lone pairs there. This moves out as a lone pair. We didn't do anything here or here. Every resonance structure has the same net charge. If this is minus, this needs to be minus. Where's the minus? We now have here. That's a neutral oxygen, 2 bonds, 2 lone pairs. We can keep going. These electrons could come here and these could move out. Everything is shown by arrows. These move in to make pi bond. These move out to put lone pair here. We didn't do anything here. That's a minus. We can do one more resonance structure. These electrons move here. These move out. Pi bond here, here. Lone pair there. Now if I bring these in, what do I do here? Move pi bond out. Don't go moving any sigma electrons. Right? Pi electrons out. What does that do? What does that arrow movement do? It gives this back. 4 total resonance structures. Which one's major of the 4? If you look at them, they all have 3 pi bonds. So it's not number of bonds. Which one's better? Would you rather have minus on oxygen or carbon?
Carbon.
Doesn't have minus on oxygen. Oxygen's more electronegative. What's another reason this one's better? You've got the nice benzene ring. That's a little bit up for argument, but typically right there. Which is more stable? The phenoxide anion or this standard alkoxide anion? Yes. Resonance delocalized, resonance stabilized. The charge is spread over many atoms. This is an isolated anion. It's not delocalized. Thus, which one of these is more acidic? This should be reviewed from week 2. Which one's more willing to become minus and give up the H plus? That one. More willing to become minus because it would be resonance delocalized. The one on the left would be an isolated anion. It doesn't want to become that as willing. Phenol is about 1,000,000 times more acidic than cyclohexanol. But phenol is not as acidic as a carboxylic acid. Questions about stabilizing anions? Let's see what's on the flip side. We'll go back to neutral molecules, but neutral molecules containing heteroatoms. Heteroatoms mean non-carbon. being able to show resonance structures of a neutral molecule like this is important for predicting reactivity and illustrating a number of other things. The resonance of this is just like the resonance of the O- we showed previously. Difference is this is neutral. That really doesn't matter. You just got to keep track of charges. The similarity is this atom has a lone pair that we can do resonance with. Well, here it is. That nitrogen has a lone pair we can do resonance with. Now there's no charge. If there's a charge, that says look to delocalize the charge. Here, the lone pair on the header atom is a good place to start. And we can say these electrons will move in and these out. Show in your paper what that gives, including correct charges. This arrow moving in, we now have what between nitrogen and carbon? What's the charge on the nitrogen? Positive. What do we now have on this carbon? And charge? Good. There you go. This is net neutral. So resonance structure has to be net neutral. We can keep going with the lone pair. These electrons can move here and these out. Get here. And these electrons move here and these out. Now if we move these in and move the pi electrons out on the nitrogen, we would get back to here. Which of these four resonance structures is major? First one, why?
Because there are less charges.
Because what?
There are less charges.
Less charges. No formal charges, no charge separation. Charge separation is not as good. Also, we start destroying the aromatic ring to a degree. This is your major structure. But the hybrid what type of charge is on this nitrogen in the hybrid, in the true structure? What type of charge is there? Partial plus. Question, which carbons of the ring have partial minus? As a result of the resonance, the resonance donation of the lone pair here, which ones? No, not all of them. You see that in your resonance structure. That one, that one, that one. Partial minus there, and partial minus there. All of them is not, I mean, there's donation all through here. Yes, but in terms of resonance and actual where the minus falls, that's sort of another question. And here, and here is your answer, because there's things that happen with such a molecule here, and here that is predicted by this right here. If you could take a picture, a Polaroid picture of this molecule, you would see some high electron density here, here, and here as a result of this lone pair being donated into this ring by resonance. Question to do on your own. Basically, we just answered this question. This is here. That's aniline. If you remember aniline, a functional group, aniline, that itself is called aniline. Aniline is a starting material for indigo. Anybody got blue jeans on today? The blue color was made starting with aniline. About 17 billion tons of indigo are made each year, starting with aniline. Here's aniline with a ketone group added. Question: which amino group of the two compounds above is the most electron rich? You need to draw all resonance structures and then sort of see if you can rationalize this question. How do you answer this question from the resonance structures? Please work on that. Delocalization of pi bonds to heteroatoms. This is another common resonance theme or approach. A pi bond can be polarized. Early on, we polarized just an alkene. I said we maybe can move it here and maybe get lone pair here and a plus here. Resonance. I also kind of said, well, there's really no dipole here, so this is not like really easy to do, and why would you want to do this? Here we have a heteroatom pi bonded as opposed to just two carbons. Here we have a dipole. This oxygen is a greedy polar. And the pi electrons are more easily polarized than sigma electrons. These pi electrons can actually be moved up onto the oxygen. What would you get? What does this arrow give? You move them up. Show that. What does that arrow mean? Pi bond is moving up onto oxygen as what? Third lone pair. That's now a minus. What is this? That's a positive. So this illustrates the common polarization of a pi bond with a heteroatom towards the heteroatom. You would never go this way and put minus here and leave that as a plus. By the way, if you made that oxygen a plus, it would not have an octet. And what happens if you leave oxygen or nitrogen or halogen without an octet? It will hunt you down. Maybe when you're asleep, maybe when you're having lunch, it will not be happy. That oxygen's happy, it gets the electrons. Polarization. True structure of the carbonyl, hybrid. Bond and a half between here, partial minus, partial plus. Every time you see a carbonyl, that's what it really looks like. Of course, this is your major structure because there's no charge separation. But this contributes some. Show all possible resonance structures of the above cation. Go ahead, do that. Show all possible resonance structures of the above cation. Fluorine has 3 lone pairs. These electrons can move in here. We draw a resonance structure there. How do you stabilize a cation? Move electrons towards it. Lone pair. Boom. Any other resonance structures possible? Any others? Amber?
Oxygen, negative.
Made the oxygen negative. What do you mean? How we do what? What arrow movement?
Move it up around the oxygen.
Here?
Yeah.
Move it up?
No, down to the,
Move it this way?
yeah.
Like a windshield wiper down? What does that give?
We want to do an oxygen negative charge.
How many lone pairs on the oxygen? How does that give another lone pair on? This would not put another lone pair on oxygen. We're just moving this down. That would move this here. Is this what you're going to show? There would not be another lone pair on the oxygen. This oxygen would be plus. That oxygen is going to hunt you down. That oxygen doesn't have an octet. It only has 6 electrons around it, no octet. That is not a good resonance structure. This is pulling this way. This oxygen is pulling. These electrons are being pulled towards that oxygen. These electrons are not going to move down. You only never leave oxygen without an octet. If this was a carbon up here, we could do this. Because carbon doesn't mind being left without an octet and being positive. Oxygen, nitrogen, halogen, never leave it without an octet. But the more important thing is here, why did you think there'd be a third lone pair up there? There would not be. This does not indicate that. This is pulling electrons down. So we need to understand the arrow movement. The reason I asked to show this is this right here, because I see you guys trying to draw resonance structures like this. So oxygen does not have an octet. No good. Don't do it. Understand your arrow movement. There was only one additional resonance structure there. Lone pair of the fluorine donating. Effect on acid base. We already kind of touched on this when I showed you the phenol and the cycle of these two. This is a million times more acidic because the anion would be resonance stabilized. We consider the anions here. Worse resonance delocalization stabilizes this. No resonance. Carboxylic acid is even more acidic. It's a million times more acidic than this. What type of resonance do we have here? Electrons here, electrons up. Like in, out. We get here, I'm just going to call the ring R. Bond and a half, partial minus, partial minus. When we did resonance structures of phenol, how many total resonance structures can you draw of phenol? Nava?
4.
4 total. We had the original and then we drew 3 for a total of 4. 4 resonance structures here. How many can you draw of carboxylic acid like this? 2 total. So which is more stable? 4 resonance structures or 2? You may think that 4 would be better. More resonance structures, more charge delocalization, yes. But the pKa implies that this is not as stable as that. Why not? More resonance structures, why is it not as stable? More acidic means the anion is more stable. Does anybody know why? When we did resonance of this, what atom did we put the minus on in phenol? Carbon, carbon, carbon. Carbon doesn't like minus that much. It's not that electronegative. Over here, where are we putting the charge at? It's on oxygen. Where do we put that over here? Oxygen. 2 oxygens is better than 1 oxygen and 3 carbons. The charge is being able to be putting it on another oxygen, where here you're putting it on another carbon. Yeah, there's 3 of them, but apparently that's not as good as that because we see it in the numbers. Don't think just because there's more resonance structures it's more stable. What type of atom are you dealing with? The charge is on 2 different oxygens. That's why it's so stable, more acidic than this. This is more acidic than that because we do have resonance there, resonance delocalization. Question to do on your own. Which of these phenols is more acidic? Draw resonance structures to answer them. Typically, more delocalization the better. Unless you're just putting it on carbon with another one, you can put it on oxygen. Other questions? Basicity. Which is more basic, ppF 10 or 5?
10.
ppF 10, more basic. This is for the conjugate acid. Weaker conjugate acid, stronger base. Hopefully you'll be able to look at these and say this is more basic. Why is this nitrogen more basic than that one? So Tia, why is this nitrogen more basic than this one?
Well, looking at pKa, the pKa is higher. You mentioned single bonds in the ring at least.
This means it's more basic. Why is it more basic?
The pKa number is higher.
This lone pair is isolated. Is this lone pair sitting right on nitrogen, or is it delocalized into the ring? We've already done resonance structures of this. In fact, we did a hybrid of this. In the hybrid, what type of charge is on that nitrogen? Partial plus. There's partial plus here. How eager is a partial plus nitrogen going to want to bond to an H plus? No. There's a number of ways to argue why this is less basic. Lone pair delocalized by resonance. That lone pair is really moved all through here into the ring. We've already drawn resonance structures. This lone pair is sitting right here like boom, 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 boom. You know, it's like, hey, I want a proton, here I am. This one's spread out all through here. This guy's actually non-basic. And there's a question here because back in week 2, I said anytime a lone pair is in a p orbital, it's not going to be basic. That lone pair is in a p orbital. LP in p orbital. And early on I said it's non-basic. Well, this is slightly basic. Because it doesn't want to disrupt the aromaticity, so it's somewhat localized. but not as localized as that one. Over here, what type of orbital is that lone pair in? It's the same thing. But here, there's a very prominent resonance structure. Because of that greeting oxygen, electrons are being pulled here. These electrons here, these electrons up. I'll just call that R minus plus. These electrons are pulled to that oxygen, and we get, there's a lot of positive on that nitrogen. Okay, we're out of time here. Please answer the questions below. Resonance structures. There's several here to draw resonance structures of. Next time we'll be moving on to the chemistry of dienes. I know you've been dying to get to this portion of the material. Please take a look. Information session about Prestige tomorrow at 1 o'clock. You can't get 17,000 if you don't apply. I guarantee you. If you don't apply, you won't get it.